We're going to demonstrate the image classification pipeline. The image classification pipeline refers to problems which are about image input data being classified into one or more categories. Here, for example, we have a data set which we're classifying into 4 different categories of animal images. So the kind of tests we perform on the image pipeline include things like the bias testing by looking at class ratios, testing for explainability, testing for security, testing for privacy as high-risk tests. Then we perform coverage-based tests and performance-based tests. So the idea is that we need to perform end-to-end testing of any model, and the input given to this kind of a testing engine is the model output as given by data scientist and the test data. Based on these two, we generate these tests. So let's look at the first of the tests, which is the explainability. So in explainability, we look at 2 kinds of explainability. One is using techniques of white box explainability. We try to explain the notion of focus in the image where the model is looking at. So if you look at here, if the focus of the image is farther away from the main object of interest, and that's what is causing the misclassification of actual animal being 1 class and being put as 0 class. Similarly, we also look at how we can use the black box technique, which are using perturbation techniques of basic input data. We try to find out the sensitivity of the parts of the image to the classification, and we find out what is the focus, which is the green area here, which is basically what the model is looking at. And that's the primary reason why we see a misclassification. And this misclassification focus gives to the data scientist an insight into how they can change unwanted data, which is distracting the model away from focus. So that's the main goal of explainability. Then we look at security testing, where we try to simulate attack vectors on the original data by creating adversarial attack on the original image, which the classifier is fooled into thinking of a different class than the correct class. So this kind of attack can be both kind of white box as well as black box. And the idea of using this kind of a approach is to simulate all possible adversarial attacks, whether black box or white box. But the idea is, given the original data, we try to generate the corner cases, which are basically attack vectors, which are usually like a simulation of what hackers would try to attempt on the system. The next comes the notion of privacy testing. This is a subset of the original notion of what we call a security testing, where the goal of hacker is not to fool the model, but to steal the data, which is private data about individual records on which the model is trained. And this is what we do in privacy testing, is to simulate the privacy attacker and try to identify the reverse engineered input data from the model. So here, for example, we're able to discover certain input data by running the privacy attack simulation, and our test of privacy is actually generating these corner cases from a privacy perspective. But then what happens in privacy generated input reverse engineered data is that just discovering this input data is not enough. If suppose any of them has actually PII, like a face or an SSN or an age-related information, etc., we have to be careful, and we will typically pass the reverse engineered data of the privacy test through a PII check, if any of them, and that leads us to a potentially scenario where model has to be redone by taking into account PIIs to be properly masked before applying the training. And then from bias perspective, we feel the relative percentages of distribution of classes is what is going to give you the perspective of the bias with respect to the class. So we have done testing for explainability, testing for security, testing for privacy, testing for bias. Then from coverage perspective, our goal is primarily to look at 2 things, either having generated corner cases based on perturbation of the input data, on different dimensions and capturing the test scenarios where the model is performing badly. Those become corner cases. And this is what we call metamorphic testing based black box coverage techniques. The other one is where we look at white box technique, especially for deep neural network kind of architectures, where we try to reverse engineer the model and try to find out those paths in the neural network which are not covered adequately and generate those corner cases which trigger those paths which are not covered. And those lead to the corner cases. So we can discover corner cases both by white box as well as black box. And corner cases, as you can understand, are basically like security attack vectors, are those scenarios where the classifier is giving wrong results. And then we look at performance testing, where we try to look at simulation of different kinds of load and subject the system to different tests. One we say is soak test, another one is test. Soak test is where we try to see a continuous load for a long period of time. And test is where we try to see a sudden burst kind of a load. And we find the response. So these are the typical tests we perform on any image classifier. And this generated report is a result after having a backend loop, which is done on the system, which generates all the data and the required inputs for generating this kind of report. But we don't stop there. We also augment it with a feedback loop, whereby we use the output of our tests to improve the model. For example, for performance, we try to improve the model by applying quantization and improve the model performance 8x times. Same way, when we discover corner cases with both coverage and security attack vectors, what we try to do is we try to improve the performance of the model by retraining the model with a combination of original training data and the corner case images. Why? Because we want to make sure that the resulting model performs correctly for all these corner cases. As you can see here, the actual class 0 before model tuning, earlier default model which was given for test was doing wrong, but now after model tuning, it behaves correctly. And that's the power of using a feedback loop after running the test. So this is how we have across different kinds of pipelines, we have different kinds of tests. So this gives an idea of the product where we try different kinds of tests on the input model and the data, and we generate this kind of report after running a batch script on generating the data required for all these tests.